Hello, everyone, and welcome to poster 1326, Automated Hippocampal Unfolding for Quantitative Mapping, Morphometry, and Subfield Definition. So I've developed a software called Hippocampal AutoTop, or Automated Topology. Basically what it does, you input a T2 weighted image like this one, and it will give you all of these nice things, including a tissue segmentation of intrahippocampal structures, our application of our previously developed coordinate framework, which can then be used to flat map the hippocampus, which I've shown down here. Here we've topologically defined the hippocampal subfields and projected them back to this subject's native space. And then you can also extract quantitative features such as gyrification, T2 weight, or thickness. So hippocampal substructures can be better understood by explicitly modeling the folding or topology within the hippocampus. So in this example, look at these images. You can see on the left here, it's very hard to see anything in this image at all. It's quite low resolution. But as we move to the right, we get a much clearer picture of what's happening inside the hippocampus, including its folding, which I've highlighted in red here. And then if we look back at the lower resolution, hopefully you could even still understand some of the folding that's happening inside that image. So I think this makes the images more interpretable and may facilitate a lot of measures within the hippocampus. This is, of course, challenging to automate because of the complex folding and also the wide inter-individual variability we see. So here's a fairly typical hippocampus, whereas here's one with a very straight body or a very curved body. Here's one with a very small tail versus a very large tail. And here's a fairly smooth hippocampus versus a fairly digitated or folded hippocampus. So to automate this, basically we focused on the Human Connectome Project T2 weighted MRI data. First, we performed detailed tissue segmentation using a convolutional neural network. So the way we did this is using incremental learning, where basically we started with some previous hippocampal segmentations, and then we trained and then performed inference on some of the Human Connectome Project data, and we applied this successively over three steps with manual corrections to those outputs in between. So here's just one example of how that training process looks. So we then perform post-processing, which gives us then seamless workflow into our previously developed unfolding pipeline. So check that out if you're interested. So a little bit more detail on the outputs here. So you'll get a resampled and cropped image of just the hippocampus, as well as the tissue segmentation that's from the CNN of all these intrahippocampal structures. The main one of interest being this rust-colored label, which is hippocampal gray matter, which we then define these hippocampal coordinates over. We can take the anterior, posterior, and proximal distal coordinates as the axes to then index any position within the hippocampus. Here, I'm defining the different hippocampal subfields in this flat mapped or topological space. And this comes from 3D histology or 3D big brain. So we can then take those subfield definitions and project them into this subject's folded or native space. We can also extract very detailed tissue measures, such as the gyrification index, which you can see is high in the more digitated areas, T2 weights, which tend to be very particularly high in CA1, as well as thickness, which can also vary between subfields. So preliminary results can be found for most of the Human Connectome 1200 subject release. BIDSAB is coming soon, and you can follow this project on GitHub here, and also get in contact with me there. A few additional analyses here. So here's a formal comparison of the reliability of that CNN-based tissue segmentation. So we can see the main labels of interest are this gray matter, as well as SRLM. So this is high myelin laminae, basically white matter within the hippocampus. And we see very high DICE scores, both before and after this post-processing step. So generally, this was as good, if not better, than between two human interrators. We also performed a comparison to some other methods, so free surfers, hippocampal subfield pipeline, as well as automatic segmentation of hippocampal subfields, or ASHES. So we did deformable registration within the same participant between these three methods. Here's an example of one subject. So we see in the middle here our proposed method, hippocampal AutoTop, at the top, free surfer, and at the bottom, ASHES, as well as the 3D models to the right. And I'm just showing equivalent labels from each of these methods. Here are the deformations between these, so you can examine those in more detail. But in brief, what we saw is some systematic differences were larger hippocampal head at subiculum in free surfer, and smaller hippocampal tail and subiculum in ASHES. Also, ASHES and free surfer were not able to consistently capture these folds or digitations within the hippocampus. So feel free to get in contact with me. I'm happy to discuss further if you want to set up a meeting as well. Thanks, and have a good day.